Welcome to Basic Electronics. I am Mahesh Patil and I have been teaching at IIT Bombay. This course is about basic electronics, but before we start with electronics, let us make a few comments about the process of learning. This process involves three components. The first component is the teacher, who needs to present the course content in a systematic and logical manner, and we can assign 25% weightage to the teacher. Next comes the course material such as video lectures, textbooks, and internet resources. We can assign another 25% to this part. We still have 50% left, and that must be assigned to the effort from the student. The student's involvement is crucial in the learning process. If the student is learning from a recorded lecture, it is important to realize that it is very different than watching a movie or a TV serial. If something is not clear, you must stop the video, watch that part of the lecture again, work out things yourself with pen and paper, and then continue with the recorded lecture. An excellent way to learn is to prepare your own notes based on the recorded lectures and maybe other inputs. That will surely help in clarifying difficult concepts. Coming to this specific course, we will cover several useful electronic circuits in this course, both in the analog and digital domains. And our emphasis will always be on understanding the fundamental concepts rather than rote learning. So with that introduction, let us get started. Before we begin with basic electronics, it is a good idea to develop a historical perspective of electronics, see how things have evolved and so on. And we should mention before starting that the images that we are going to see have been taken from the internet. Alright, so let us get started. Electronics really started with vacuum tubes because in those days there were no semiconductor devices. And the simplest vacuum tube, the diode, shown here, was invented by John Fleming in 1904. So in this device, there is a cathode, which is a filament, and there is a plate. The plate is biased with a positive potential, and the cathode is heated with this filament supply so that it emits electrons. These electrons get attracted to the plate, and that is how a current flows in the external circuit. And if this voltage is made negative, then there is virtually no current. So this device allows current flow in one direction but blocks current flow in the other direction. So that is how this diode works. In 1907, De Forest invented the triode by inserting a third electrode between cathode and anode. Here is the schematic diagram, and this is the third electrode called grid. The way this device works is that the cathode emits electrons as it did in the diode, and the plate is positively biased. So the electrons emitted by the cathode get attracted to the plate, and that is how we have a plate current. Now the grid electrode is biased with a negative voltage, and therefore it repels these electrons, and therefore that causes a reduction in the plate current. Here is a plot of the plate current in milliamps versus plate potential in volts, and observe how high these voltages are, 300 volts. Let us take a fixed voltage, let's say 200 volts. For V grid equal to 0, we have that much current. For V grid equal to -2, the current is smaller. For -4, still smaller, and so on. So this figure clearly shows the control of V grid on the plate current. Here is what the real structure looks like. We have a glass tube under vacuum. This one, the outer cylinder, is the anode. After that, the red structure is the control grid, and inside that is the cathode. So cathode emits electrons which make it to the anode, and because of the negative potential on the control grid, some of the electrons get repelled. That's how the control grid controls the current. And the terminals, all of these, are brought out like that at the bottom. And here is a real photograph showing various types of tubes. There are tubes with more than 3 electrodes and they get quite complicated. But roughly we can see that there is a glass tube, and we also notice that they are large. This dimension could be something like 5 centimeters, for example. Alright, so this size is one problem with vacuum tubes. They tend to be very large compared to the modern semiconductor devices, for sure. The other problem can be seen in this picture. And these vacuum tubes, when they conduct, they glow like a light bulb, and we can see that in this picture. And that's the other problem with vacuum tubes. They consume way too much power. Here is a circuit diagram of an audio amplifier made with vacuum tubes. These are the tubes here. That's the speaker. There's a transformer there. And what we should really notice in this circuit diagram is this part here, 300 volts. That's a very high voltage. And in modern electronics, we simply don't have these kinds of large voltages. We probably have 10 volts or 15 volts, but certainly not hundreds of volts. Here are some pictures of one of the first computers called the ENIAC computer, built with vacuum tubes. We are talking about 1946, so there were no semiconductor devices at that time. The vacuum tubes are not seen in this picture, but they may be behind these panels here. This entire room is one single computer, and this is another view of the same computer. And these people we see here, they are probably computer engineers or computer programmers of those times. Let us now look at some facts and figures about the ENIAC computer. And there is a lot of information on this topic on the internet, and you should really look it up. Here we will just look at some of the points. It was heralded as a giant brain by the press, and giant brain it was compared to the electromechanical computers of those days. This computer was 1,000 times faster. It had some 17,000 vacuum tubes, some 6,000 manual switches, and approximately 5 million hand soldered joints. This of course was bad news, because with each hand soldered joint, the reliability of the entire computer goes down. It consumed 150 kilowatts. That's a huge amount of power. Input was possible from an IBM card reader, and each card was one statement of a program. Its clock frequency was 100 kilohertz. And for comparison, our modern computers have a clock frequency of 2 gigahertz or 3 gigahertz. So you can find out how many times faster today's computers are. Several tubes burnt out almost every day, and also these soldering joints gave problems, leaving the computer non-functional about half the time. So the computer could not be used continuously because of this reason. And what did the computer do? It could be programmed to perform complex sequences of operations, including loops, branches, and subroutines. After the program was figured out on paper, the process of getting the program into ENIAC by manipulating its switches and cables could take days. Today, once we have a program, we can just key it in with our keyboard, but in those days that was not possible. The task of taking a problem and mapping it onto the machine was complex and usually took weeks, which is a very long time. This point is very interesting. The programmers debugged problems by crawling inside the massive structure to find bad joints and bad tubes. There was really no other choice, so they had to do that. The first test problem consisted of computations for the hydrogen bomb. Alright, so here are some of the facts and figures about this computer, but you should really look up the internet, and there is a lot of other information over there. Another interesting picture about the ENIAC computer. These ladies are probably computer operators. She is carrying a program listing in her hand. She is also carrying some cables to give this other person. Now this person who is sitting is actually changing the position of the switches and making connections with the cables that she receives from this standing lady. Alright, so let us now talk about the first transistor and why was it required in the first place. The vacuum tube was a bulky and fragile device which consumed a significant power. So the US government, particularly the Department of Defense, was looking for a solid state alternative for the vacuum tube, and this job was given to Dr. Shockley at Bell Laboratories, this person sitting here. In 1947, Shockley, Bardeen and Brattain, this is Shockley, this is Bardeen, that is Brattain, at Bell Laboratories invented the first transistor. This is a picture of the first transistor, and this shows its schematic diagram. So this triangle that we see over here is actually a piece of plastic, and on both sides we have a gold foil. One is the emitter and the other one is the collector, and this whole structure is pressed on this semiconductor. In those days it was germanium, and this way a point contact was made between this emitter and the germanium, and also between this collector and this germanium. This semiconductor was called the base, and that is how we have this emitter, base, collector, transistor structure. The modern transistor looks very different. Here is a packaged device, and inside there is a single semiconductor piece which has all three, emitter, base and collector. So the emitter, base and base collector junctions are all in the same semiconductor, and that is called monolithic. Let us now talk about semiconductor technology and see how it has evolved with time. The bipolar transistor, which was the first transistor to be invented back in 1947, continues to be an important device both as a discrete device and as part of integrated circuits, that is ICs, such as op amps. However, in digital circuits such as processors and memory, the MOS, that is metal oxide semiconductor field effect transistor, has surpassed the bipolar transistor by several miles actually, because of the high integration density and low power consumption that the MOS technology offers. It is interesting to note that the idea behind the MOS transistors actually dates back to 1930, that is before the bipolar transistor was invented in 1947, as we saw. And in 1930, Lilienfeld filed a patent for field effect transistor, which forms the basis for the MOS transistor. But the MOS technology took several years to mature, and therefore ICs with bipolar technology came first to the market, followed soon by ICs in MOS technology. The first MOS IC was in 1964, and it was a shift register. Alright, in 1958, Jack Kilby at Texas Instruments demonstrated the first integrated circuit consisting of a bipolar transistor and resistors and capacitors fabricated on a single piece of germanium. So this was a big breakthrough, and around the same time Robert Noyce of Fairchild was also pursuing this idea of integrating several things on the same semiconductor piece, and he also came up with some improvements especially related to metallization. So this work was done more or less in parallel, and the rest is history, and we will see a part of that. In the next few slides, we will try to get a glimpse of semiconductor technology. This of course is a vast subject, and people have courses, 1 semester long courses on this topic, but we will only take a quick look to get an idea. The starting point is a silicon wafer, and its diameter is something like 30 centimeters or 1 foot, which is pretty large, and it is relatively thin. Its thickness is less than 1 millimeter. And after going through a series of processing steps using very sophisticated equipment, this is what the wafer looks like. This is the top view. It has got some pattern on it, and each one of these rectangles, for example this one, is one chip. Now the chip could be as simple as a single diode or a single transistor, or it could be as complex as a microprocessor with 10 million transistors or 100 million transistors. The chips are separated from each other, and each chip is mounted in a package like this one. This package is called the DIP package, but today we have very sophisticated packages with a much larger number of pins as well. Now this chip has got these little squares here, which are called the metal pads, and those are internally connected to the devices, the transistors or whatever on the chip. From this metal pad we have a metal wire bonded to the pins of the IC, which looks like this. As the end user, this package is what we see, but we should remember that a huge amount of effort, time, and of course money goes into the design and fabrication of this chip. Alright, this is what the cross section of this wafer looks like after all the processing steps are over, and we see several small regions. Here we have N-type doping, here we have P-type doping, and so on, and we will take a look at part of this, how it is done. And an important thing to note is that this entire structure, the so-called active devices, is confined only to a very small region on top of the wafer, that is only 10 microns maybe in thickness, and the rest of the wafer is simply there to support this entire top layer. Here is a picture of the silicon wafer after the processing steps are over, and we can see these rectangles here. Each one of those is going to be one chip, and notice how shiny it is. You can see the reflection of this person's hand over here, and that is because it requires to be polished to a very smooth finish so that processing can be accomplished. As we mentioned, the wafer goes through a series of processing steps. There is one important process called diffusion, in which the wafer is heated to a very high temperature such as 900 degrees or 1000 degrees, and a gas is passed over the surface of the wafer to dope it either P-type or N-type. So here is a diffusion furnace. There are these controls here to control the temperature as well as the duration of that processing step, and the wafers are stacked over here. So this whole contraption comes out, we stack the wafers and push it in, and here is a close-up. So these are the wafers. They will be pushed into the furnace. The furnace will be locked up for whatever number of minutes, and that is how this diffusion process takes place. Let us look at some more pictures of the fabrication process, and notice that we don't see any semiconductor wafers anywhere. Those are inside this equipment somewhere. Here is an operator who looks more like a surgeon in an operation theater, and this kind of extreme cleanliness is really required in the fabrication process, because any contamination is absolutely disastrous for our devices that we are trying to fabricate. For example, our body goes on shedding dead skin cells continuously without our knowledge, and if any of those cells lands up on the semiconductor wafer, then it's going to kill several transistors and the chip is simply not going to work as we want it to. Another picture, this person is taking these wafers from one equipment to another. In each equipment, a different processing step takes place, and at the end of all of that, we have the final product. Another picture, here is what a silicon wafer looks like, and you can see once again that it is very smooth. You can see the reflection of this person's face over here. Let us go through a very simple fabrication process, namely fabrication of a p-n junction diode. Here is the cross section of an n-type wafer. That means it's a silicon wafer with n-type doping such as phosphorus. We first grow silicon dioxide on that, shown there. After that we apply photoresist, shown with this purple layer here. Now this photoresist is a material which is sensitive to light. After that we place a mask on top of the photoresist, shown here in black color. Then we expose this whole thing to ultraviolet light. Now there is a window in the mask over here, so the light goes through and this part gets exposed and this part does not get exposed because we have the mask blocking the light over there. Next, the mask is removed and now we have the photoresist. Some part of the photoresist has been exposed to UV light and the rest has not been exposed to UV light. Alright, now we develop the resist. That means we dip that in a chemical. The part that has been exposed to UV light gets dissolved and goes away, leaving behind the unexposed part of the photoresist. That is followed by an etching step in which the silicon wafer is immersed in hydrofluoric acid, HF. Now this part of the oxide which is exposed gets dissolved and this part which is protected by the photoresist remains. So at the end of this step, what we do is strip the resist. That means we dip the wafer in some other chemical which removes this photoresist. And that is followed by a p-type diffusion step. That means the wafer is heated to a high temperature like we have seen some time ago in a diffusion furnace, and the boron gas BH3 passes over the wafer. And because of this oxide, nothing happens in these regions, but where there is no oxide, the boron atoms get inside, and that makes it p-type. So now we have p-type semiconductor here, and our original sample was n-type, so we have a p-n junction. After this, metallization is carried on. That means one contact is made to this region and another contact is made to this region. So that is how we have a p-n junction diode. Let us now talk about scaling of MOS technology, which has been happening over the years. Shrinking of the smallest definable dimension, also called the feature size on the chip, has enabled a huge number of transistors to be integrated on one chip. As this size per transistor reduces, what it means is we can pack a much larger number of transistors in the same area, and that is how this number of transistors per chip has been going up. Here are some figures. In 1970, the feature size was 10 micron. In 2010, it was 0.032 micron, so much smaller. And here is a plot of the feature size versus year, and note that this is a logarithmic scale. So in the 70s, we were talking about feature sizes of a few microns, and in 2010 it is less than 0.1 micron. And as a result of the steady reduction in the feature size over the years, the number of transistors per chip has been going up correspondingly. And here is a plot. This is the number of transistors per chip, and that is the year. And note that this scale is also logarithmic. This is 1000 transistors per chip. This is 10,000. This is 100,000, 1 million, 10 million, and so on. In the 1970s, we were talking about a few thousand transistors per chip, and now around 2010 here, we are talking about a much larger number, something like 100 million transistors per chip. So this increase is really very dramatic. All right. Now, Gordon Moore of Intel predicted this kind of trend in 1965, and his prediction was that the number of transistors will double every 2 years. And this prediction has turned out to be more or less accurate over several decades, in fact, and it has become known as Moore's law. All right. Now, what is the practical implication of all these developments in the semiconductor industry? In the 1970s, we were talking about probably a few hundred gates per chip, and now we have much increased functionality possible, and we can talk about system on a chip, which is much more complex than what we used to have in the 70s. Let us consider a vacuum tube computer built with 1 million tubes, and we should emphasize that such a computer has not been built. We only want to know what it would look like. We find that there are several difficulties, and let us see what those are. First, each vacuum tube would occupy an area of 5 centimeters by 5 centimeters roughly, and when you multiply that by 1 million, that area of course turns out to be very large. It's like a football field. Second, each vacuum tube consumes, let's say, something like 1 watt to 10 watts of power, and therefore when we multiply that by 1 million, we are talking about a total power in the range of megawatts, very large power. Now this power, which is in the megawatts range, a very large power, turns into heat, and that has to be removed. If we don't remove the heat, then the computer temperature will keep rising, and finally things will melt, smoke will come out, and so on, which of course we don't want. The next issue is reliability. This kind of computer will have very poor reliability because it has a very large number of vacuum tubes and soldering joints. And what it means is that this computer is going to require very frequent maintenance, because every half an hour or 1 hour some tube or soldering joint is going to go bad, and that will need to be fixed. And finally, even if it was actually built, the speed would be much lower than a modern CPU because of parasitic capacitances and inductances of the cables that we're going to use for the connections. All right. So here is what the computer would look like, and we must emphasize once again that it has never happened. Nobody has really built such a computer. It will be large, and it will have to be housed in a building of this kind. One. Second, it's going to consume a huge amount of power, and therefore we'll need to get a separate connection from the state electricity board coming like that. So that is our power supply. Third, such a computer is going to require a massive heat sink, and the only practical way of removing such a large amount of heat is to immerse the whole computer in a waterfall so that the water keeps taking the heat away on a continuous basis. And finally, we are going to require a maintenance department, to be located on the same premises, because some tube or soldering joint is going to keep failing and we need somebody to attend to that. So we require a 24/7 service for this computer, and the best way to do that is to have somebody right on the location. All right. And now compare that computer with the mobile phone that you carry in your pocket or your purse. So that was a short review of how electronics has progressed so far, and now it is time to get down to the basics and understand how things work. So see you in the next class.